Good evening, gentlemen and ladies. Welcome to ISTRT, one more CPD topic of February. As most of you know, Mr. Thuc is our senior fellow and our member of Institute of Structural Engineers, and is a chartered structural engineer. Basically, we have today's topic is Ciel Tower, Dubai Marina. It's about one more high-risk topic for today. Just to introduce about Mr. Thuc, is a registered structural engineer from Vietnam, as well as Dubai municipality, and his interest towards high-rise structures and mixed-use developments. He did his master's degree and his lead AP as well. Thuc is currently leading the structural engineering department for NOR Consultants. Welcome, Mr. Thuc, and the floor is yours.
Yeah, thanks, Sama, for the introduction and the opportunity for me to speak about Ciel Tower in Dubai Marina. In this CPD talk tonight, I will firstly speak about the project overview, then cover all major structural aspects from site condition and design challenge, from form finding, shape optimization to structural system development, from wind and earthquake engineering to foundation design construction and superstructure design construction. I will also discuss sustainability before making conclusions and moving to Q&A section. So let's get started. These are a few facts. The client is the first group, TFG in Dubai, and NOR is the architect, structural engineer, and MEP engineer for the project. The construction of foundation started in May 2019, and the building is expected to complete in September 2023. This is a reinforced concrete building, and the tower is constructed of reinforced concrete, and structural steel is used as a secondary material. The reinforced concrete design is done to ACI 318, and steel design and composite designs are complying to AISC 360. The general contractor for the construction is China Railway 18, and China State Construction Engineering Corporation is the specialist steel contractor. The enabling work is done by GTAS and Dutch Foundation. Above them, both the companies are in Dubai. For people who are not very familiar with the geography of Dubai, the site is in Dubai Marina, close to the entrance to Palm Jumeirah, and it's about 20 kilometers from the Burj Khalifa in downtown Dubai. The plot is about 3,600 square meters. It had a trapezoidal shape and is in between the Cayenne Tower. This is the Cayenne Tower. It's in between the Cayenne Tower and Ansufu Road and the vehicular bridge that's crossing the marina. This is the route plan. So the tower and podium are designed to maximum the views to Palm Jumeirah, the Arabian Gulf, and the marina. The total built-up area is slightly more than 100,000 square meters. This building is now under construction. At the time we take this photo, the tower core is at level 12, and the top slab is at level 8. This is a typical hotel floor. It has a rounded shape. The floor width and the floor depth, together with the width of the atrium, these three parameters, they are varying along the height of the tower. The center core hosts the elevators and escape stairs, MEP services, and the radial shielders are placed between the hotel rooms. While most of the super tall buildings are mixed use, and this is a hotel building, there's no office and there's no residential apartment, it's just hotel and amenities. The floor to floor height is 3.5 meters, and there are totally 1,042 keys in this hotel. There are 12 garden terraces and 12 HR between the garden terraces on the north side of the floor plate, and all of the garden terraces are facing Palm Jumeirah. These are the panoramic elevator that runs all the way from ground to level 75. And these are the typical interior design of the hotel room. So our theme for interior design is based on wabi-sabi, which is a Japanese philosophy. It promotes the beauty of imperfection, impermanence, and simplicity. These are building sections from the base. We have ground floor and basement that hold the front of house, back of house, and MVP areas. The main drop-off is on level 1, so level 3 to level 9 are parking floors. Level 10 hold the main kitchen, and level 11 is the leisure deck with infinity pools and landscape. So along the height of the tower, there are 3 MVP floors. They are at level 21, and level 54, and level 73. Level 76 hold a horizon bar and infinity pool, and level 81 with the top floor is an observation platform. This is the view from Ansufu Road. So the road curves before leading to the vehicular bridge. The tower would appear right in front of the windshield when you arrive to Dubai Marina. For site condition and design challenge, firstly, I would like to speak about a few project milestones. So on the 10th of April 2018, NOR starts working on the concept design. Prior to this date, the client had been developing a tall residential building on the same plot for which the shoring, excavation, and piling work were completed on 31st August 2017. Due to the market correction, this project that I call Project X were cancelled and all the site activities were suspended. NOR is then approached by the client to design a super tall hotel tower, utilizing the existing ball price. And we have been continuously working on the design for a year. And on 27th of May 2019, the construction restarts. On the 1st October 2019, we obtained piling permit from Dubai Municipality. And on 22nd January 2020, we received the structure permit for foundation and superstructure. On 2nd November 2020, we obtained the full building permit for architecture and MEP. This is the photo of the site taken in early 2018 during our first field visit. The site is fully excavated. The existing shoring system comprises of diaphragm walls at the perimeters of the plot and circular steel compression struts between the diaphragm walls. Bore price, including testing, pie head breaking, have all been completed. This is the foundation plan of Project X. So the structure system includes 2 rectangular cores and 8 mega columns on a 3.5 meter thick raft foundation. And the tower layout is planned in northeast direction, and so is the pie layout. This is a 3D view of Project X foundation. And this is the Ciel Tower that NOR designs. It had a center core, 11 radial shear walls, 2 columns, and the structure arrangement is completely in north-south direction. The challenge for us is that how to design a super tall tower, which is significantly taller than Project X, utilizing existing bore price and complying with the site condition and constraint. We soon realized that we are in trouble because the Ciel Tower is 60 meters taller. There would be a higher gravity and lateral load at foundation. The Ciel Tower configuration makes the existing pies highly unfavorable. Many pies cannot be fully utilized. So in case we need new pies, we are left with limited space because of closed space between the existing pies. And lastly, because of some complications that are associated with the excavation and shoring works, and the local authority requests the developer and NOR not to do any deeper excavation for the new building. So those are our solutions. Firstly, we look into reduce the gravity load. We investigate different primary materials, various column grids and floor framing systems, plus the lightweight architectural components. We also minimize the lateral force. So for wind, we run the workshop on form findings and shape optimization with our design architect. For earthquake, we perform a probability seismic hazard analysis to assess the real seismic activity of the site. We also put in new piles, so we employ a 3D geotechnical modeling and analysis for the piles and foundation. Besides assessing the pile load and sediment, it helps us to assess the pile geotechnical capacities when the pile spacing is less than 2.5 times the diameters. Yeah, and lastly, when we design the foundation, we follow the existing excavation levels. We use a slightly thicker rock to effectively distribute the load to existing piles. About form finding and shape optimization, this is a study led by design architects with input from structural engineers and wind engineering specialists. The purpose is to arrive with an iconic building and minimize the wind force acting on the structure through the envelopes. So this study is done by CFD analysis. We investigate 5 different architectural shapes for the tower under predominant wind in northwest direction. The first 4 shapes, you can shape 1 to shape 4A. They are all 320 meters tall. Shape 4B is 20 meters taller at 340 meters. The podium configuration is the same in all 5 different shapes, and the total build-up area for the project is also the same in 5 different shapes. So the 50-year wind speed for the CFD analysis is 45 meters per second in compliance to Dubai municipalities regulation. We use a gradient wind profile for this CFD analysis, but there's no dynamic properties, there's no surrounding structure. This is the CFD analysis results for shape 1, the rectangular prism. We could see very large wake region behind the towers. This is the result for shape 2, it's a square prism. This is the result for shape 3, it's a rotated square prism. And this is shape 4A, it's a taper cylinder. This shape has minimum wake region behind the building. This is shape 4B, it's a taper cylinder plus the crown and the opening in the crown. This shape is 20 millimeters taller than the other shapes. Again, we found small wake regions and less turbulence behind the tower. Let's watch a short animation of wind path line around shape 4B. Yeah, so we then compare the base shears and base moment of 5 different shapes. If we assume the base shear and base moment for shape 1 at 100%, shape 4A is the most efficient shape. Base shear is about 50% of shape 1, and base moment is around 45% of shape 1. Shape 4B is also efficient, despite being 20 meters taller. The base shear and base moment are about 60% the values in shape 1. So this shape is then selected for further development. And this is the final configuration of the building after concept design. The tower is 366.5 meters above the ground with 5 design elements: a basement, ground floor, podium, the towers, and the crown. This is a day view from Palm Jumeirah and a night view. About moving to structure system development, these are 3D views of our final Revit model. At the base, we have ground floor, basement, and the foundation, and the podium is between level 1 and 11. And this is the tower, and this is the crown from level 76 to top of the building. So along the height of the tower, there are 12 garden terraces and archway between the terraces. All of the garden terraces are facing Palm Jumeirah and the Arabian Gulf. The reinforced concrete outriggers and bell walls have been placed at 3 MEP floors at level 21, level 53, and level 73. So the structural system of this building, in a short sentence, is the building wall system enhanced by reinforced concrete outriggers and bell wall. During the concept design, we investigate different structure grid, material, floor framing systems, and work with the QS team for an initial cost plan. We then rule out the steel and composite design because of high cost. We select reinforced concrete as the primary material. So the tower core is holding the elevators and escape stair MEP services. There are 11 radial shear wall between the hotel rooms and 2 columns beside the atria. A typical floor includes 200 thick reinforced concrete slab inside the center core and at the corridor, and 240 millimeter thick post-tension slab outside the core. To minimize the gravity load, the post-tension slab is optimized to reduce the cell weight and while still meets the requirement on deflection, and of course have a reasonable reinforcement ratio of around 75 kilogram per cubic meters. On the facade, on the atrium side, we have the steel trusses and tension cables to support the atrium facade, and we have the steel frames that support the panoramic elevators, which run all the way 300 meters from ground floor to level 75. To further reduce the gravity load to foundation, we use lightweight partition throughout the buildings. So we've been using dry wall with a density of 400 kilogram per cubic meters. Where we need masonry block, we have been using lightweight masonry block with 1100 kilogram per cubic meters density. And then we also use lightweight floor screed with 1800 kilogram per cubic meters. The total superimposed load for the typical floor is 4 kilonewton per square meter. This is also the minimum requirement for residential buildings by Dubai municipality. We also study an alternative, which is the voided flat plate system with plastic void former for the hotel floors. This system provides 10% reduction in cell weight for typical floor slab, which is equivalent to around 2.5% reduction in total cell weight at foundation level. However, it has a few disadvantages. Firstly, there are limited suppliers in the local market, and there are limited contractors who had experience in this system. Secondly, it's basically designed at an RC slab, so the system requires slightly longer slab construction cycle compared to post-tension slab because labor areas had more rebar fixation, and also the concrete had to be done in 2 stages. So finally, we don't select this option. This is a typical hotel floor with a garden terrace between the panoramic elevators and the external atrium facade. Level 21 is an MEP floor. There are 8 deep reinforced concrete outriggers between the radial shear walls, and the center core. This is the framing plan of level 21 because the perimeter core is relatively thin compared to the size of the outrigger beams. So we provide reinforced concrete beams locally along the perimeter of the core to ensure a good connectivity between the outriggers and perimeter core. When we combine level 21, which is an MEP floor, and level 22, which is a hotel floor directly above, we have a complete system of outriggers and bell walls. The reinforced concrete slab for level 21 and level 22 are 300 mm thick, and in 2 floors there are 16 reinforced concrete outriggers. The depth of the outriggers is between 1.5 meter to 2.2 meters. At the perimeter, we have a 750 millimeter thick reinforced concrete bell walls that connects 2 floors. Of course, we provide rectangular openings on the bell walls for ventilation. This is a 3D view of the tower crown. So the center hole is called the eye of the needle. It is a design feature, but also has to reduce the wind force acting on the superstructure. The crown is about 60 meters tall from level 76 to top of the building. It has two reinforced concrete core and steel moment frames on the perimeter to support facade. The frames are placed into the cores at every 10.5 meters. Level 76 hosts a horizon bar and an infinity pool. Steel posts are placed on top of the perimeter reinforced concrete beams that are spanning between the shear walls. This is a wonderful view from infinity pool on level 76 to Palm Jumeirah. You could clearly see that the Atlantis, the Palm, which is also a north project between 2005 and 2010. Level 81, the floor structure comprises a 200 thick metal deck concrete slab on top of steel beams. The beams are spanning between the reinforced concrete core. So on the north side and the south side, there are two steel trusses. They are spanning between the corner columns. So this is the framing plan of level 81. You could see two steel trusses here. They are curved in plan, and they are placed back laterally to the core. Yeah. Level R1 is the roof that supports BMU machine. This is an architectural rendering for the podium. It is a design intent to float the podium above level 1 through a series of V-shaped columns. It is to create an impressive drop-up and entrance to the hotel. So going down from top of the podium, this is level 11. It is a leisure deck with two infinity pools and landscape. And this is a 3D view from infinity pool on level 11 toward Palm Jumeirah. This is a typical parking floor. So the framing of the parking floor includes a 5-meter long cantilever slab on the on the left. It is supported by post-tension band beams, which are 600 mm deep. And the floor-to-floor height 2.9 meters, and the beams are 600 mm. So the clearance underneath the beam is exactly 2.3 meters, which meets minimum requirement by Dubai municipality. So there are 4 planted columns. They are circled on the slide. The planted columns sit on transfer beams at level 3 and level 4. So these planted columns support 8 floors above level 3. On the right, the 300 thick post-tension slab is sloping 5 to 7% and is connecting to the upper floor. This is level 3, the first parking floor. There's the location of the transfer structure. Yeah. On framing plan, we have 4 transfer structure at those locations. The most critical transfer structure is the 10.5 meter cantilever structure at this location. It supports a planted column, which again receives the load for 8 floors above. So this is the elevation of that structure. It includes a 2.5 meter deep reinforced concrete beam with diagonal steel brace to control the deflection. In the podium, each pair of the podium columns is supported on a V-shaped column underneath, which is between level 1 and level 3. So this is a 3D view of level 1, which is it hosts the drop-up lobby and also a column 3 outdoor terrace, just beneath the transfer structure. So the floor-to-floor height for this floor is 10.5 meters, and on this side we have 6 V-shaped columns. On this floor, we also have the ramp coming up from ground floor to level 1 and ramp from level 1 going to level 3. This is ground floor. It hosts the front of house, back of house parking and MEP area. The reinforced concrete slab is 300 mm thick. This is the basement which hosts the MEP services and water tanks. Around the perimeter, we have a retaining wall which is 400 mm thick. And these are the three structure models that we use in design. We use ETAP model for checking the global stability and reinforced concrete design, and the SAP 2000 model is used to design steel elements. And finally, MIDA chain model, which we prepare at the end stage of the design. We use it to validate the global stability and the design of few critical elements. We found that the results are consistent between the three different software packages. These are the first three mode shape from a model with uncracked section. So mode 1 is a translation mode with a period of 10.4 seconds. And mode 2 is also a translation mode in a perpendicular direction with a period of 9.2 seconds. Mode 3 is a torsional mode with a period of 3.5 seconds. These are mode number 4, mode number 5, and mode number 6. The first 6 modes in this building accounts for around 60% of mass participation. So, but in design, we consider totally 36 modes, which account for 99% of mass participation. This is a 3D model of the tower crown. Going to wind and earthquake engineering, that is, as you may be aware of, the design of tall buildings in Dubai has been regulated by Dubai Municipality Circular 191, which was issued in 2013. The circular sets the parameter for wind and earthquake design to ASCE 7 and UBC 97. This is the basic design wind speed for this project is 45 meters per second, according to the Circular 191. These charts are from a local wind climate study. And according to this study, the predicted 50-year wind speed for Dubai would be 38 meters per second. So 45 meters per second will be equivalent to a 400 years return period. Which is, so in design, we've been complying to DM Circular 191, and we'll be using 45 meters per second, pretty conservative. Just an update for the engineers in Dubai that we just today received a DM Circular, circular number 37, 2021. In this circular, the 50-year design wind speed is reduced from 45 meters per second to 38 meters per second. So it is a very good news for us. In the wind tunnel test, we consider 2 configurations of the surrounding. The photos on the left show the existing surrounding, and the photo on the right show the future surroundings in Dubai Marina. We then compare the wind base shear and base moment from wind tunnel test, cost-based calculations, and result from CFD analysis. So we note that the CFD analysis gives the most conservative result for both base shears and base moment because it doesn't consider the dynamic property of the building or the shearing effect from the surrounding buildings and structures. For serviceability, we consider a damping ratio of 1.5%, and we found that the maximum inter-story drift of the tower is less than the allowable limit of H over 400 or 0.25%. The maximum lateral displacement at the top of the tower is also less than the allowable limit of H over 500 or 700 millimeters. For acceleration, we investigate the tower structure under 1% and 1.5% damping ratios. Acceleration and torsional velocity in both scenarios are well below the allowable limit for residential buildings, so we don't need any supplementary damping system for this tower. About the earthquake engineering, this is my favorite chart. The seismic provision in UBC 97 is based on an inelastic force and an inelastic force deformation curve. So we basically calculate the elastic base shear VE based on the first mode period and assuming a linear elastic behavior of the structure. And then we take the elastic base shear divided by the system over strength factor R to obtain the inelastic base shear for design. And if the structure has a transfer element, then again we multiply this inelastic base shear by an omega factor. This is the over strength factor to get base shear Vy, and we use Vy for designing the transfer element. The seismic requirement for this building is zone 2B, and R factor is 4.5, omega 0 is 2.8. Again, I would remind Dubai structural engineers that the DM Circular 37/2021 and that includes new seismic design parameters for tall buildings in Dubai. To determine soil profile, we conduct 3 cross-hole seismic tests during the geotechnical investigation. The 30-meter average shear wave velocity is 940 meters per second. This indicates a soil profile SB according to UBC 97. Just a brief about the regional tectonic plate. The Arabian plate is moving north at a speed of between 2 and 3 centimeters a year. So when it collides to a Eurasian plate and Indian plate, it creates the Jacquard thrust and flow belt and Makran thrust belt, which are the 2 major sources for earthquake in the region. However, if you look into historical seismic activity with a magnitude more than 4.5, this since 1900, the majority of UAE, Qatar, Bahrain, and eastern part of Saudi Arabia are in the low seismic zone. So we perform a probabilistic seismic hazard study, and we obtain the response spectrum curve for surface level earthquake, design earthquake, and maximum considered earthquake. If you notice that the design earthquake in this chart, it had a return period of 475 years, which is the same one in UBC 97. So in this graph, we plot the design earthquake in green against the UBC 97 response spectrum curve for zone 1, zone 2A, and zone 2B. So I would say the real seismic activity in Dubai is close to zone 1, but the regulation says design for zone 2B pretty relatively conservative. With 5% damping ratio, the maximum inter-story rip and the seismic load are less than the allowable limit of 2%. This is according to UBC 97. This is a comparison of base shears and base moment from earthquake and wind to reflect the load factors in combination, and the wind force and moment are multiplied by a factor of 1.6. So the graph shows that for the superstructure design, the design is governed by wind, except at the very top part of the tower, the seismic moment is slightly larger than the wind moment. In the design, a field member is dominated by seismic load. This is called the higher mode effect. You know, the higher modes with short periods are corresponding to larger acceleration. If you could remember this, if you could remember this graph, yeah. So when the period is short, then it means that the spectral acceleration is high. Yeah. So moving to foundation design construction, this building is founded on pile foundation. Piles take 100% of the load. We ignore the soil bearing capacity underneath the raft, complying to DM's regulation. To support the tower, we put in 22 additional piles. 21 of them are 1.5 meter in diameter, with compression capacity of 37,000 kilonewton and a length of 48 meters. And we put in one meter diameter pile with a capacity of 11,000 kilonewton and a length of 29 meters. So there are totally 175 piles under the foundation. This is a 3D view of the foundation. Under the tower, we have 122 piles, and all of them are 1.5 meter in diameter. Under the podium, we have 47 piles. 20 piles are 1.5 meter in diameter, and 27 piles are 1 meter in diameter. This is the foundation plan with various thicknesses. So the tower raft generally is 4 meter thick. When the raft is folded to accommodate elevator pit, then the thickening zones is between 7 and 8.7 meters. For the podium, the raft vary from 1.6 to 2 meter to 3 meters. And we also have isolated pie cap in this part of the podium. And the pie cap is 1.6 meter deep, and the podium raft slab is 500 mm thick. The retaining walls around the perimeter of the basement is 400 mm thick. And this is the cross section of the raft. You could see that the raft is actually folded different levels, because we have different requirement for service elevator, for passenger elevator, for panoramic elevator. And we also follow the existing excavation aside. So to analyze the raft on the last group of piles, we performed soil structure interaction study with several iterations of pile stiffness between the structural engineer and geotechnical engineer. So the purpose is to determine the pile spring constants of a large group of piles for pile and foundation design, and also for estimation of foundation sediment. So here is the structure model with piles and raft with various thicknesses. We model the foundation in SEP and also in ETAF model. The raft profile is really complicated for this project because of the existing covered levels and different requirement for the elevators. This is the geotechnical models in a plastic 3D foundation. The geotechnical engineer models rafts, piles, soil and rock layers, and the reaction from the superstructure are provided by structural engineers. And this is a geotechnical section. So the soil and rock parameters are taken from geotechnical investigation report, and underneath the raft, we have basically 3 layers. The first layer is medium dense and dense silty 5 to medium sand and gravel. The SPD number is between 11 and 49. Second layers, which is in yellow color, it is very dense 5 to medium sand and gravel with some calcareous fragment. The SPD number is slightly more than 50. And lastly, we have the extremely weak to very weak, weak to hard calcareous sandstone conglomerate. They are interbedded. The rock quality definition varies from 0 to 100%, and unconfined compressive strength varies from 0.1 to 17.9 MPa. The estimated foundation sediment is about 50 millimeter at the center of the core, with maximum sediment, differential sediment of around 15 millimeters, and the angle of rotation less than 1/1000. So everything is good. We monitor the foundation sediment during the construction. We put in 5 monitoring points under the tower raft, and 2 monitoring points under the podium. Measurement is reported to engineers with us on a monthly basis for a period of 36 months. This photo shows the temporary work for the construction of new piles. Firstly we need to protect the existing debris from the piles by capping up the reinforcement. So, and the second step, we partially backfill the site to create a piling platform, and then we provided an access ramp from the street down to the temporary platform. Then we do the piling from the temporary platform. After that, we take out the backfill again. we've been designing the foundation using high performance concrete. The concrete cylinder strength for the tower raft and podium raft is 60 MPa and 50 MPa. We use triple blend concrete. Triple blend concrete mixes with 50 to 55% GG, 50 to 55% GGBS, and 5 to 7% micro silica. We maintain very low water to cement ratio, like this is 0.6 for the tower raft and 0.3 for the podium raft. But we request for very high slumps, up to 700 millimeters. So the main advantage of high performance concrete is firstly to saving casting time and labor cost. And secondly, we want to maintain a consistent concrete quality and uniformity, especially for the areas with high river congestion. And lastly, we wanted to reduce vibration and noise, especially for concreting at night. The foundation is constructed in 3 stages or 3 pours. Pour 1 is the green zone that you see here. This is the lower part of the tower raft. And pour 2 is the tower raft, the upper part of tower raft, plus the podium raft on the left side of this pour strip. And pour number 3 is the podium raft on the right side of the pour strip. Let's watch a short video with information about pour number 1. So pour 1 includes 2,500 cubic meter of concrete, and it takes 14 hours to complete. You see the quality of concrete is excellent. Yeah, and this is a photo of our design team during a field visit to witness pour number 1. The structural engineer in this photo doesn't seem afraid of COVID-19. He was just smiling in front of the camera. So pour 2 is done on 8th of August 2020. It includes 7,000 cubic meter of concrete, and it takes 48 hours to complete. This is the largest pour that we have done for a single tower raft. In the right sky view, we did a larger pour of 11,000 cubic meter, but that is for 2 separate tower rafts. Pour 3 was completed on the 30th August 2020. We put in 1,300 cubic meter of concrete, and it takes 14 hours to complete. So the total volume of concrete for the foundation is 10,800 cubic meters, and total tonnage of rebars is 3,300 tons. So the reinforcement ratio is around 300 kilogram per cubic meter of concrete, including starter bars. We also monitor the heat in concrete during aeration, because when the internal concrete temperature is high, there is an increased potential of delay adrenite formation, which is a material-related issues that can lead to severe cracking. To avoid this, usually we keep maximum internal temperature of concrete at 80 degrees Celsius. So if you look at the chart here, even though the raft is 4 meters thick, but the maximum temperature is just around 75 degrees, which is good. Going to the superstructure design construction, in this project, reinforced concrete design is done according to ACI 31811, and steel and composite design is done to ISC 36010. For the vertical elements, concrete cylinder strength is 70 MPa for the first 100 meters of the towers, and then the neck part of the tower, neck 120 meters, the concrete cylinder strength is 60 MPa and 50 MPa for the remaining structure. The rebars is of grade 500B, so the yield strength is 500 MPa. For ductility and detailing, we comply to the ACI provision for ordinary reinforced concrete work and intermediate moment frames. We also use high performance concrete for superstructure. We also use triple plant for the vertical elements. The percentage of GGBS is between 26 to 36%, and microsilica between 5 to 9%. We maintain also low water cement ratio, as you could see on the chart, and a very high slump. They are mixes that we've been using for most of our tall buildings in the UAE. Those mixes had a great workability for pumping up to more than 300 meters. We also done the long-term vertical shortening analysis according to ACI 209, and the graph on the right shows the vertical shortening values for half of the pond on the floor plate. The maximum expected shortening is around 80 millimeters, and it's happening in this L-shaped column. Pond number 1 is also having around shortening around 70 millimeters. So in general, we provide compensation of 5 millimeter at every 5 floor. And this is the long-term horizontal displacement. So as you could see, the displacement in X direction is not critical. This is X direction, and this is the deflection in X direction, because the tower is symmetrical. So the lateral movement due to long-term shortening of the vertical element is not critical in this direction. However, it is critical in Y direction, because if you look at the floor plate, we have a 300 meter tall atrium here on the north side of the floor plate. So the center of mass tend to be on the close to the south side, and the tower will be moving in Y direction, around 40 to 50 millimeters. This movement will be compensated by adjusting the jump form and to provide horizontal cambering for those floors. We also monitor the strain and vertical shortening in concrete walls and columns using strain gauges in combination with optical survey method. We use Yelkin 4200 strain gauges. They are embedded in the concrete walls. You can see the location of the strain gauge on the plan. We monitor the strain and then calculate the vertical shortening for a period of 36 months. There are 12 atria and garden terraces along the height of the towers. This is just an atrium between the two garden terraces at level 68 and level 74. And this is the layout of the garden terrace at level 68. So this atrium is around 27.5 meters tall. It is naturally ventilated through the louvers at these locations. The structural system that support atrium facade includes firstly horizontal steel trusses. They are 1.2 meter deep, and they span 80 meters between the L-shaped columns. And the trusses resist lateral wind pressure. And we have also the vertical cables that take gravity load from the glass panel and transfer it to the reinforced concrete beam at the garden terrace above. So the front cables are 60 mm thick and 16 mm in diameter, and they are every drawn. They take heavy gravity load from glass panels, and the cable at the back of the truss are 12 mm in diameters. They are at alternate joint mainly to brace the bottom chord of the trusses. So in design, we designed the steel trusses in an isolated model that you can see on the left side of the slide. And then we provide pin connection with standard oversized hose at the end connections. However, we also consider additional load from the tower that's going to be put on the truss. During an extreme seismic event. So when the tower rotates, it imposes additional compression force into the truss, and we check this by modeling all the trusses and vertical cable in one 3D models. So that in design, the demand capacity ratio is a summation of the demand capacity ratio from isolated models and the one from the complete 3D models. So by doing this, we ensure that the facade system is intact, during any extreme event that could happen. So this is a typical V-shaped column between level 1 and level 3. We have a truss action here. The diagonal column resists axial compression force, and the connecting beam resists tension force. Concrete is not good in resisting tension, so we design a steel section which is embedded inside the concrete beam to take 100% of tension force and 100% of the shear force, because when the concrete is in tension, the shear capacity reduces. This is the photo of the V-shaped column site. Vertical rebars are being installed. And this is the construction of 10.5 meter cantilever structure at level 3. So as you know, it supports a planted column, and this planted column supports 8 floors above. So to avoid lock-in stress in steel diagonal brace due to vertical shortening of the shear wall and the column, we do full welding at one end of the brace, and the connection at the top end will be fully welded after completion of level 15 floor slab. And then after that, we can remove the temporary prop underneath the beam. Going to sustainable engineering, you know that the building industry produces 50% of the global greenhouse gas emissions. So to reach zero carbon emission goal by 2050, we must look at the embodied carbon more seriously. The structure of a building accounts for about 50% of its embodied carbon. It means that the structure that we build are responsible for a significant proportion of global gas emissions. It's estimated that our profession is now responsible for around 10% of all energy-related carbon emission worldwide. So therefore, structural engineers, we are essential players in the fight toward carbon neutrality. And you know that the Carbon Leadership Forum had issues structural engineers 2050 challenge, which is inspiring engineers to work toward embodied carbon benchmarks while contributing data along the way. And this is a split of emission from a building life cycle from modules A1 to module C4. There are 3 processes that contribute greatly to total emission. This is firstly the product stage, which is modules A1 to A3 contribute around 50%, and the use modules B1 to B5 contribute 20%, and lastly the operation, which is module B6 and B7, contributes 23% to the emission. So module A1 to A5 is also called cradle to practical completion, and it contributes 55% of total emission. So in order to reduce the embodied carbon of structure, we need to know where we are. So for Ciel Tower, we run the calculation of structure embodied carbon for module A1 to A5. So we gather carbon factors of concrete mix, rebar, post-tension strand, and structural steel from various environmental production declarations, and that we obtain from the local manufacturers and suppliers in the UAE. We then estimate material quantities using the structure models, Revit model, and also the BOQ. The calculation is actually straightforward. The embodied carbon equals material quantity multiplied by carbon factor, and the carbon footprint equals embodied carbon divided by built-up areas. For Ciel Tower, the structure, the total structure embodied carbon is 98,260 tons CO2 emission, which is close to 100 kiloton CO2 emission. And you remember the total built-up area is slightly more than 100,000 square meters. That's why we get a structure embodied footprint of 965 kilograms CO2 per square meters. And this chart is showing the distribution of the contribution of different structural components. Like we have 741 kilogram in superstructure, 112 kilogram in foundation. In piling work, we have 74 kilogram, and for substructure and temporary work, which is diaphragm wall and compression steel truss, we have 21 kilogram and 16 kilogram accordingly. So the contribution of the superstructure is around 77% into the embodied carbon footprint. This is because it's a super tall tower, so there's a lot of concrete in the superstructure. So how large is the carbon footprint of 965 kilogram CO2 emission? I'm giving you two numbers. Firstly, the carbon footprint for a return flight between London and New York is 1,000 kilogram CO2 emission per economy class passenger. And second number is the structure embodied carbon footprint for simple and standard buildings is between 200 and 600 kilogram CO2 per square meter. So, you know, if we take the total built-up area of Ciel Tower and spread it horizontally into a three-story reinforced concrete structure with 9 by 9 column grids, so the carbon footprint could be well within this range. But Ciel Tower is a super tall building. So how to benchmark the design of Ciel Tower to the tall buildings that are existing or recently completed? We unfortunately don't have many data for tall buildings in the UAE. Especially for super tall buildings. We then refer to the carbon footprint benchmarking data for buildings by David Collins, published in the Structural Engineer issue of December 2020 for comparison. So the first graph here is it is showing the total structure embodied carbon versus roof floor area or the total built-up areas and building types. There seems to be a linear relationship between the total embodied carbon and the gross floor areas. And this is the Ciel Towers with total embodied carbon close to 100 kiloton with total built-up area slightly more than 100,000 square meters. The second graph shows the relationship between structure embodied carbon, number of stories, and the building types. This doesn't show a clear relationship between structure embodied carbon and the number of stories. The last graph is the relationship between building embodied carbon footprint in ton of CO2 emission per square meter versus number of stories and the building types. There's one building that has more than 100, by the way, the structure embodied carbons are shown in the black circles here. So there's one building that has more than 160 story. I guess this could be Burj Khalifa. The structure embodied carbon footprint for this building is about 1,600 kilogram CO2 per square meter. And this is our Ciel Tower at 965 kilogram CO2 per square meter. So we would need a lot more data to be plotted to confirm whether there is a relationship between the embodied structure embodied carbon and the number of stories. I would like to show you a proposed structure carbon rating scheme by Will Unknown, Mike Cook, and others. It is published on the Structural Engineer issues of October 2020. It is based on the estimated module A1 to A5 emission of the primary structures. So the average carbon footprint is set at 350 kilogram per square meter on the 1st October 2020. And the solid curve shows the global average targets going to carbon neutrality in 2050. And there's also upper bound and then lower bound, which are 40% better than average and 40% worse than average. In order to achieve the target of carbon neutrality by 2050, we need to target a reduction of 10%, 5 to 10% every year. It can be done through a combination of lean design, efficient use of materials, and harness the latest technology to make the concrete and steel greener. For conclusions, I would say Ciel Tower is a challenging project for both design and construction. The design team has overcome various challenges and successfully delivered an iconic supertall tower utilizing existing ball piles. The architectural vision is well achieved. The structural engineer has demonstrated a significant role within an integrated design team. The structural solution is safe, efficient, and economical. And at NOR, we are committed to sustainability.
Thank
you. A lot of design construction work for Ciel Tower happens during COVID-19 lockdown in Dubai. This shows our great resilience and discipline of the team. So I would like to thank the team members for their effort on the project. We believe the Ciel Tower will be completed on time. And lastly, these are 10 toilet hotels by 2023. 7 of them are in Dubai. NOR is proud to have designed 2 of them, the Emirates Towers Hotel in 1995 and Ciel Tower in 2020. This is also the end of my presentation. So it's over to you, Sama.
Thank you, Mr. Thuc, for your 360-degree presentation. I should say that, from concept to sustainability to construction, you covered a big topic in a short time. That much I can say. Good, friends. If you have any questions, I'm sure Mr. Thuc can take some questions. You can post it in a question and answer. One question has come from Mr. Mohammed Tariq. Did you use 80 KSI 560 MPa steel bars in the project as recently allowed ACA 31819? What could have been the savings in carbon if this was used?
Sorry, can you repeat the question? Yeah.
Actually, the steel grade which you adopted is 560 MPa.
500, yeah.
500, okay. Yeah. So not 560. So what you are saying is if you use 560 MPa, what would be savings in carbon footprint?
Well, you can also do that, but you have to remember that nowadays, in the local market, it's very difficult to look for some other different type of steel grade, rebars. So I don't think the previous rebar grades like S460, I think S460 is no more available in the local market. And I think we have only option with, to work with the S500B, grade 500B for the rebars. So we didn't do that exercise, to be honest. So.
Okay. But in general, you have basically generally as engineers, we limited to use 460 MPa. It has got a point. As engineers, we better to use actual, the steel strength which are used, which are adopted as per the metal test certificate. Yeah.
Yeah, okay. Exactly.
Yeah. Next question is Mr. Krishna Prasad Menon. Did you observe any relative settlement between the new piles and existing piles?
Well, firstly, I have to say that when we took over the site, we didn't inspection of the existing piles. We also review all the documents, as-built documents, design, calculation, test reports. So firstly, we are confident that the quality of the existing piles is good, right? And then when we put in the new piles, we've been using the same length, same capacity, and even same reinforcement. So the piles are uniform, yeah, and we don't expect any difference or settlement between the new pile and the existing pile because there's no load that has been applied to the existing pile yet.
Okay. A question from Mr. Henrik. Did you run the CFD analysis in-house or internal team?
So we work with a specialist to conduct the CFD analysis on the 5 different shapes, right? The purpose of this exercise is just to get initial ideas on how efficient our structure is, how efficient the shape of the building is. We're not relying on the CFD analysis for the final design forces. Yeah, as you will see, I've tabled three different set of base shear and base moment from wind tunnel test, coast base design, and from the CFD analysis. Yeah, we know that CFD analysis gives conservative results because there's no structural property, there's no consideration of the surrounding buildings. So it's conservative, but we just compare, like apple to apple. We compare the 5 different shapes, with CFD. We pick one, deploy it, and then calculate the coast base wind force, and then we do the wind tunnel test for that one. Yeah.
Just continuation to that, little bit high end. CFD analysis performed. Is it based on large eddy simulation or Reynolds average Navier-Stokes? I don't know. This is little hi-fi.
Yeah, actually, it's done on a software called OpenForm.
OpenForm. What is okay? Okay, good. So that's a special system. Yeah.
Yeah.
Again, see, what would you have done if there are cracks in the raft after 4-meter thick concrete pour? Did you find any cracks after 4-meter thick raft? Is it
no, we couldn't see any crack at the moment. So, but we keep monitoring the settlement. I guess that if there's a crack due to settlement, then it will have to appear. It would appear at the later stage, not now. Yeah.
Okay. A question from Mr. Madhav Reddy. Wind tunnel test is applied both in translation and rotation. Of course, yeah.
Yes, so we get a set of forces from the wind engineering specialist. Basically, there is a larger force in 2 directions and torsional moment of the tower at every floor. So yeah.
I can see 1 minute. There are some questions. Yeah. Okay, a question from the truss which you for the cladding which you designed. There are cables which you mentioned 12 mm, 16 mm. Yeah. How it will take is, you said dead load is taking the cables, which is looks to be a little lesser size for such a height, for such a load. Is it designed or is it just a concept?
Yeah, so let me explain this. So basically, we have the steel truss which is just behind the glass panel, right? So the glass panel is fixed to the top cord of the truss. I call this one the top cord of the truss, which is holding the glass panel. And then, so the weight from the glass panel will be transferred to the truss, and it will be transferred to the vertical cables.
Okay.
And the cables will be transferring the gravity load to this beam on the garden terrace above. Yeah. So in design, we design the tension cables using the tension only element in analysis. Yeah. And as I said, we have a separate isolated model that you see on the left side of the screen, and then we also model the cables and steel truss in complete 3D model. So we capture both scenarios.
Okay. The last question I'm taking now. Is it okay to share your mail ID or contact details if further questions?
Yeah, yes. So, okay, if you have any question that we couldn't cover tonight because of the limited time, please feel free to send an email.
Yeah.
Note to my email address on the screen, and you can also visit NOR regional and global websites for more information about us and about our projects. Thanks everyone for attending this CPD talk.
Good. Thank you, Mr. Thuc. And just to brief about our events in coming months, we are trying, next event is Museum of the Future. We are trying to arrange. And second is we are planning to have a CM workshop session for our graduate members who are planning to write exam in April. And friends, I'm sure some of you must have received invitation for a CM workshop. Who are interested, please again you can contact us, and you can refer to istruct.org for new people who don't know about the institution. istruct.org for memberships and information. If you have any questions, you can approach me or Mr. Abdullah. Abdullah, thank you very much. You want to add anything, Mr. Abdullah?
Thank you very much. Thank you, Thuc, for the great presentation as usual.
Yeah. Thank you, Thuc. Thuc, this is a great presentation. I think we should take up sustainable topics separately. If I can see in this part of the world, as a ISTRUCT guidelines and direction, we need to develop sustainability knowledge between among all of our engineers. I request you to consider that topic in future. Mr. Thuc?
Yeah, thanks. I was just thinking that in the region we have more than 100 members for the UAE regional group. So if each of us, when we design a building, if we spend some time doing the carbon footprint calculation, we can contribute the data, and maybe at a later stage this graph could be completed.
Good. Thank you, Thuc. And Mr. Abdullah is our technology person behind it, as usual. Thank you, Mr. Abdullah. Thank you all for attending the session. Good night.
Thank you, Samar and Abdullah. Thank you, everyone.
Good evening.
Thanks, everyone.
Bye.
Bye-bye.